What's up, guys? This is Mr. O'Brien again, and this will be part two lecture of the idea of atomic number and isotopes. And in this lecture, we're going to focus on isotopes, on what is isotopes. So this is a part two lecture. So before we start with the content, I want you to consider a classroom of sophomore students, like the one you're in, right? And I want you to think about this question. Are all the students in the classroom, at least in this classroom, are they all the same? If they're different, what differentiates them? So these are important ideas to understand because this essentially can also be analogous to isotopes. Now, before I get into the idea of what is isotopes, consider the students. Well, what makes them the same? Well, what makes them the same in this case is that they are all sophomores, right? And so if they're sophomores, they're all probably they're all in the second year of high school, right? They're all probably going through the same classes, right? More or less. They're probably all going through the same experiences in the high school that maybe a freshman doesn't have, or maybe a junior doesn't have, or maybe a senior doesn't have, right? Clearly, you guys here, all these guys here, are all sophomores, and they're not like, again, they're not like any freshmen. Okay, it makes them unique. So there's no freshmen, they're not seniors, right? They're not juniors, right? Because these guys would be, fourth year class. This would be a third year class, right? And this is your first year class, right? So each of these guys are going through different experiences, right? So all you guys are the same because you're all sophomores, right? But that's not cool if you guys are all sophomores. If I could just call you, hey, you sophomore, or hey, you sophomore, or hey, you sophomore. That's not cool because all you guys want a name, right? So we hence have to differentiate. In class, I call you by your name. But in chemistry class, the way we call out isotopes is a little bit different. So let's go back to this idea on what is isotopes. So what makes them different in this case might be that they're boys versus girls, right? That's the obvious, right? It could be the ages are different, right? 14-year-olds. We have some 15-year-olds. We have some 16-year-olds. It could be the masses of all of these people. Maybe we got some students that are 100 pounds. Maybe we have some students that are 110 pounds. Maybe you have some students that are like, 90 pounds, whatever the case may be, right? Maybe they have different masses. So there's differences here in the class, but yet there's some similarities. And this is the idea of isotopes, right? That there are differences in a certain element, but they all share a common similarity. So with that said, let's jump right across to our content. So isotopes essentially are elements that contain the same number of protons, but are different in the number of neutrons they have. So if you think about this banana for a second, right? And you might have, if you're an athlete, you might know that, hey, man, your coach tells you, hey, go eat a banana before you, go out and play or exercise. It's because bananas have this source of potassium. It kind of helps alleviate muscle cramps, right? But did you know that the banana has various types of potassium atoms? It's not just one potassium atom. It's got these three types of potassium atoms. And these three types of potassium atoms are categorized as an isotope, right? These essentially would be your sophomores, your different sophomores that have maybe a different mass or a different age. So what makes them in chemistry isotopes? Well, again, they're all potassium. They all behave the same way. Well, what makes them different in chemistry? It's because some are heavier than others, right? Well, let's keep going on this idea. Well, what makes them behave the same way? Well, the idea what makes them behave the same way is something that we identify as a protons, right? They contain all the same number of protons. And because they contain the same number of protons, they're all considered potassium. But what makes them different in the mass is the neutrons. Yes, the neutrons is what makes them different from the mass, right? Because remember, the mass of the atom is found inside this tiny little nucleus, right? That's where the mass is at. So again, to recap, what an isotope is in chemistry is that they are variations of an atom that contain the same number of protons, as you can see, but the different number of neutrons, which essentially adds to their mass, right? So we have 3 different atoms here, all found in bananas that are relatively the same, but different in their mass, right? So how do we identify each of the various isotopes present? For instance, the question would be, well, how do I identify you in my class? I can't call you a sophomore. I got to call you by a name. So these guys also want to be called by a name. They just don't want to be called potassium. So there's 2 ways we differentiate them. We first talk about what their name is. Their name is not only just potassium, it's also potassium followed by the mass number. And the mass number is what we identify as the number of protons and neutrons in that nucleus, right? So in here we have 19 protons and we have 20 neutrons. Hence we call this atom potassium 39, that isotope. This isotope will be called potassium 40, right? Because it has 19 protons and 21 neutrons. This atom will be called potassium 41 because it contains 22 neutrons and 19 protons. So again, the idea here is that they all contain the same number of protons. That's why they're called potassium. But what's different is their mass. Like you guys. You guys are all sophomores, but what makes you different in my class maybe would be your mass or your age, per se. How else can we identify these isotopes? Well, we have a symbol in the notation, in which the symbol notation has the mass number in addition to the atomic number. Now, you might be wondering, well, why do we have to identify the atomic number? Isn't that the same as a symbol? Yes, yeah, you're right. I mean, K is always going to be 19 protons, right? But we want to get in the habit of knowing the symbol because when we start writing nuclear equations, we're going to need to know what this symbol represents, okay? So with that said, take again a quick stab at these questions here. See if you can figure these out. And if you have a hard time, hit me up in tutorial. So how do we count the subatomic particles present in isotopes, right? Well, this is kind of like a rehash of what we kind of learned in the last lecture in part 1. We're now going to talk about how do we identify the protons, neutrons, and electrons inside an atom. Well, if you know your atomic number, you know you have a number of protons, and you know the number of electrons because the atom is neutral, right? And you know that the mass number is a combination of protons and neutrons because these are both in the nucleus, right? Now, if we move on and we go over this example, the question is, can you tell me how many protons and neutrons there are in this isotope of neon? Well, let's first talk about what we know about neon. Neon has atomic number of 10. So the atomic number of 10 tells us that you also have 10 protons. So check. Now that we have 10 protons, we also know that we have 10 electrons because the number of protons will equal a number of electrons because the atom is neutral, right? Now, we also know that the mass is 22. So if we have the mass is 22, right, we know that the mass consists of the protons, which is 10, and our neutrons, which in this case, we don't know what our neutrons are, right? We have no idea. So if we subtract 10 by both sides, we'll find out that our mass is or our neutron value will be 12. So 12 plus 10, right, will get you 22. Now, how do you write this symbol? Now, we can write the symbol in 2 ways. We can write the name of it, which is neon-22, or we can write the symbol, which is neon, N-E, 22 at the top, and 10 at the bottom. So that's how we write our symbol. Atomic number below, mass number on top. Okay. So now if we go to, let's see, we can go to next slide here. I want you to try these problems out, see if you can figure out what the answers are. And if you have a hard time with these, hit me up in tutorial and we can work them out together. Now, another question about isotopes is where do we find these isotopes? Well, you find them in bananas, right, for potassium, but is that only place you can find them? And that's not true. In nature, we find all the isotopes as mixtures of isotopes. So anytime you find something in nature, like an element like sodium, it's not just going to be one atom. It's going to be a mixture of various types of sodium. And where you find the mixture doesn't really matter. Where you find the element doesn't really matter because the mixture, no matter where you find it, is going to be relatively the same proportions. We call this proportion the natural abundance, right? It's essentially the amount of isotopes that you can find in nature in a certain proportions. So let's go back and continue talking about potassium. So potassium is found in these regions identified in blue. Large producers. They're found everywhere, but mostly in these areas that produce them. And the potassium is can be mined, and it comes out as this rock called salvite. And inside salvite, you'll have three types of potassium present. One called potassium 41, one called potassium 40, another one called potassium 39. But if you notice the proportions of potassium present in here is not all equal. It's not like 33% here, or 33% there, and 33% there. It's actually a certain ratio. And this ratio is unique to each element on that periodic table. So no matter where in the world you find potassium, you're going to find potassium in these quantities. Okay? You're going to find a whole bunch of potassium 39 mixed in with just a little bit potassium 41 and just even a little bit of potassium 40. So you'll find a whole bunch of these guys, right? And you'll find traces of these guys, just traces, and you'll find a little bit more traces of these guys here, right? Because again, this is your potassium 40, which is this little sliver right there, and this is your potassium 41. Okay, so the idea here is that there's a natural abundance of a certain types of isotopes present, and these natural abundances are in the mixture of those isotopes. So the question would be, why do we see the one number that represents all potassiums? Well, this goes back to our first question, right? When I identify all you guys as sophomores, you guys are different, right? But imagine an administrator coming into my classroom and asking me, hey, O'Brien, I need to know what is your average age of your students in your class, right? I can't tell them, hey, there's 14, 15, and 16-year-olds because this person only wants to know one number, right? So what number can I tell them? Well, I got to figure out what the age of my classes are. So in one of my classes, I think I remember that I had like a whole bunch of 15-year-olds and hardly any 16-year-olds. So if you give you an example, like if I had 15, 16, and 14-year-olds, I think I had like 30 kids in my class who were 15 years old. And then I had like roughly 4 or 5 kids or 14-year-olds. And then maybe I had one kid that was 16. So when I actually come up with an average of these numbers, the average of these numbers comes up around 14.8, right? Or 14.89 or something like that. It's not quite 15 because there's some 16-year-olds, and it's definitely not quite 15 because I got some 14-year-olds. So this number, this average, I would tell my administrator that that's kind of like what my class looks like. But that is not true for any actual kid in my class because you're either 14 or 15 or 16. That same idea is essentially the idea of why this number exists, which we call an atomic mass, right? That atomic mass is a representation of all the of all the isotopes of that element, right? So if you take a look at potassium, recall that our potassium came in different abundances. We had a whole bunch of 39, and we had a really small amount of 40, and just slightly more 41. This number reflects all of these, but really shows you which one of these becomes more naturally abundant. Essentially, clearly here that this is telling you anywhere you find potassium in the world, you're going to have probably more potassium 39 in your hand than any one of these guys, because there's way more potassium 39 present than any one of these isotopes. It's a weighted average. The key word here is weighted, not the middle number. Make sure that you understand that. It's not the middle number. It's a weighted average depending on the amount of isotopes present. So let's continue on with this idea in this example. I want you to think about this question. Now, this question identifies that you have in an element X, right? Calls atomic mass, that comes at a 7.5% abundance and a 92% abundance with element of a mass of 7. What would the atomic mass of this element X look like if you were to have a periodic square with an element X? What would this number look like is the question. Well, we first need to understand, again, these abundances. It clearly tells us if we had a pie chart, right, that our pie chart would not be 50-50. This is not 50% element of 6 mass and 50% of element 7 mass. That is not what you see here. This is not right. Rather, what you see is you see a pie chart, or envision a pie chart, that has about 92%, right? 92.5% of a substance that has a mass of 7, and a small amount of it that has a mass of 6, right? So because there's way more element that has a mass of 7, our average will need to be close to 7. Now, it can't be 7.0 because there's still some 6 in there that brings it down, right? And it can't clearly be 6, right? Because there is way more 7 than there is 6. So what does it look like? Let me erase all this. Well, what the pie chart looks like is this. And what our mass is going to be that. About 6.941, which clearly kind of shows you that there's way more element that has a mass of 7 than a mass of 6. And if you look on the periodic table, you can identify that, hey, it's not going to be, it's not going to be helium, because helium has a mass of 4, average atomic mass of 4. And it can't be beryllium, because that beryllium has an atomic mass of 9. So your closest answer is going to be 6.9, and it's going to be lithium, right? So try these problems out. See if you can figure those out. And then if you have any questions, hit me up at tutorial. Thanks.